Alright, hello physicists. Today we're going to continue on in our quest to understand electric fields, and we're going to introduce one of the very useful approximations, that of the electric dipole, which is just a plus charge and a minus charge that are separated by a little bit of distance, and so we'll talk about that in a second. So today we're going to review acceleration of charges and equilibrium. We're going to talk about some of our electric field special cases that we did last week, including the ring of charge and the disk of charge. We're going to introduce a very old sort of way of thinking about visualizing electric fields, that being the field lines. In fact, this dates back all the way to Michael Faraday himself, the English book binder turned chemist, who is the now seen as one of the forefathers of field theory. And then we're going to introduce the dipole field, the dipole energy, and the dipole torque. So we're going to talk about all of this stuff. Now remember from last time that we've now moved on. We started out with electric forces, which were just saying you have two particles. They can either pull each other together if they have opposite charges, or push each other apart if they have like charges. So that was Coulomb's law. And now we've moved on to having the idea, the thing that's pulling on an electric charge is the electric field. So, for instance, if I have an electric charge here, a plus charge, and then I put another charge there, I can write the electric field in terms of how far away from the particle that I'm sitting here and the charge on the first particle. So I could even put a Q1 there. And then I can talk about the electric force on this particle. So this could be my Q1. I can talk about the force on this electric particle Q2. And this is equivalent at this point to just restating Coulomb's law. But I'm thinking about it in a different way. You have the electric field that's doing the pushing and pulling, and it's stretched because there's another charge around. Now, here's a nice conceptual question to help us remember what we went over last time on on how forces cause acceleration. Okay? Now, remember, F equals ma, so the same amount of force will accelerate a particle with less mass more. So, for instance, an electron has a mass that's much, much less than that of the proton, even though they have the same charge. So it turns out it's easier to accelerate an electron than it is to accelerate a proton. Okay, now it says here, suppose we have an electron and all of these different charges that are being accelerated. And it first tells us an electron E having travels through a small hole in plate A, so there's a tube or something there, and then towards plate B. A uniform electric field in the region between the plate then slows the electron without deflecting it. What is the direction of the field? Okay, so the electron is moving in the plus x direction. It's moving to the right, and it slows down, so that means that the force has to be pushing back on it, slowing it down. And the interesting thing about this is that if the force on the electron, which has a minus charge, if it has a minus charge, that means that the electric field is going to point opposite the direction of the force on that minus charge, because the sign on this hangs around. So the electric field in this region points in the plus x direction. So the force on the electron is in the minus x direction. The electric field is in the plus x direction. Then the question asks us, 4 other particles similarly travel through small holes in either plate A or plate B, and then into a region between the plates. They have charges plus the positive charge, and negative charge. So that's this, and that. The fourth, labeled N, is a neutron which is electrically neutral. Does the speed of each of those particles increase, decrease, or remain the same in the region between the plates? Well, because we know the sign on these charges, we can tell what direction the force is going to be. So for this one, it's a positive charge, and so the force is going to be in the direction of the motion. It's going to speed up. On the other hand, this Q2 is moving backwards through the field. The force is in this, it's in the plus direction, but it's moving the minus direction, so it will slow down. And then Q3, on the other hand, is a minus charged particle, just like that electron. So it is going to have a force in the opposite direction, but that's in its direction of motion, so it will speed up. Okay? So we have speed up would be our plus Q1 and our minus Q3. And then we'd have slow down. That would be our E, our electron, and our minus Q, our plus Q2. Now, the sort of funny one is this neutron. A neutron does not have an electric charge. Therefore, we're going to have to say that the force on it is 0, and therefore it just stays the same. So our neutron stays the same because electric force only acts on particles that have electric charge. Okay, now another idea that we talked a bit about in previous videos is that idea of equilibrium. Equilibrium happens when the forces on an object sum to 0. So if there's a force pushing right on it, there also has to be a force pushing left on it. You know, we've talked about this in terms of gravity pulling down. You can have electric force pushing up, something like that. Another idea that we've only briefly touched on is that of stable or unstable equilibrium. A ball that's sitting at the bottom of a bowl, if it's just acted on by gravitational forces, is in equilibrium at the bottom. But if you rock it out a little bit, it will just go back and forth. So the forces then, when you displace the particle, cause it to go back toward its equilibrium point. So this is a stable equilibrium. On the other hand, if we turn the bowl upside down and then put the ball on top of it, there would be equilibrium at one particular point if you have it just exactly balanced. Another example of this is balancing a pencil right on its tip. On the other hand, but it's unstable, so any slight little push, any perturbation in physicists' language, would cause that ball to fall off. So if there's no preferred direction, physicists would respond would call that a spontaneous break of symmetry, yeah, so that gets advanced more quickly. On the other hand, in this other example right here, there's just one point where the slope is 0. And in that case, your unstable equilibrium does have a preferred direction. So that's sort of an interesting distinction between those two cases. Now, okay, and just to give you another nice example of this equilibrium, we could have, for instance, a alpha particle be pulled down by the force of gravity and be pushed up by the electrical force, and that could be a way to get equilibrium. And so in this case, they tell us what are the magnitude and direction of the electric field that that will balance the gravitational force on the particle. Well, if your Fe equals your Fg, your electrical force equals your gravitational force, then you have to have QE minus mg equals 0. So your E has to be pointing up in this case. So E is pointing up because the Q is positive, positively charged. It's the nucleus. And so what we would have here is 2 little e times E minus mg equals 0. And then you can solve that by putting in your numbers. So your E magnitude would be just mg over 2e. And in this case, that m would be 6.64 times 10 to the minus 27th kilograms. And then our electric field, or sorry, our gravitational field strength here on Earth is 9.8 newtons per kilogram. And then we have this 2e is the E is the that 1.602 times 10 to the minus 19th coulombs. Okay, so ultimately you're going to have units of newtons per coulomb on a question like this. I gave one on the homework that's very similar to this. Okay, now we want to give ourselves as many tools as possible to be able to visualize these sort of electromagnetic phenomena. And one of the oldest ways of visualizing the electric fields is actually from the inventor of field theory. Michael Faraday is this fellow right here in our picture. A very interesting figure in the history of science, devoutly religious, never got an education, and he was a bookbinder who happened to get a job as preparing experiments, and kind of worked his way up. And so he was extremely good at doing electrical experiments, but didn't know math. And so he would draw these pictures, and he would imagine lines of force surrounding particles being the thing that caused these various electromagnetic phenomena. And so he was the one to introduce this idea of there being lines of force. It seems like a little bit of a misuse of the language in terms of force, but that's okay. And the way that we can draw these field lines is if you have a plus charge, the lines are oriented, so they have a direction on them, and they're pointing in the direction of the electric field. So positive electric charges gets pushed away from plus charges and towards minus charges. So we can see that being shown right here. And the interesting thing about these field lines is that they start on a plus and end on a minus. And if you have two pluses, you know, they don't go to each other. They sort of look like they repel. So there is a way to make this more mathematical, but we're not going to do it right now. So here's an example of electric field lines, just to give you an idea. The thing I want to get across to you is that electric field lines, the strength of the electric field is related to how squished together the lines are. So here we're given an example, figure 2234. The electric field lines on the left have twice the separation of those on the right. If the magnitude of the field at A is 40 newtons per coulomb, what is the magnitude of a force on a proton at A? So force on a proton would just be the electrical force is Q times E, so it would get pulled in the left direction, in the minus x direction, and that would just be your 1.6 times 10 to the minus 19th coulombs times 40 newtons per coulomb. And if I can do that in my head correctly, I think that's going to give me 64 or 6.4, yeah, no, 64 times 10 to the minus 19th, which is 6.4 times 10 to the minus 18th newtons. Okay. And then for part B, it says, what is the magnitude of the field at B? Well, if the field lines are twice as spread out, the field is going to be half as big. Okay, so the E field over here is just going to be 20 newtons per coulomb. Okay, so I'm not going to hit this idea very hard, but I do want you to have seen it so that if you come across that in a different context, it doesn't fluster you. Okay, so in our last video at the very end, we talked a little bit about a special case. So the most important special case for you to remember is that of the the point charge for an electric field. Remember, an electric field point charge is just E equals 1 over 4 pi epsilon naught times Q over R squared. So that's KQ over R squared. And then what we did with this was we said, well, if we want to find the electric field along Z, what we can do is go ahead and realize that the electric field contribution on the two sides of the ring are going to cancel each other out in the XY direction, but not along Z. So let's just add up the electric field components along Z. So we had DE, so this is just we're treating this little line of charge as essentially a point charge. This Z squared plus R squared is just how far that little r is. And then we took it times cosine of theta. That would give us just the Z component of our electric field, and that's what we added up. So the this was the Z over R. The R is Z squared. This Z squared plus R squared to the 1/2 is this little r. So that's where this 3/2 comes from, because we already had the 2/2 plus times another factor of r. Okay, and then what we did was we integrated around the circle, so added up that whole all of the charge contributions around there, and this gave us the electric field of a charged ring, which, if you go ahead and take that as r goes to infinity, just looks like a point charge. Okay, where the Z takes on the position of the R. And then as R goes to 0, this E goes to 0. Whoop, 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 whoop. I should say, as Z goes to infinity, we get the electric field of this. You can't see that it's spread out. It just looks like it's all at a point. And then as Z goes to 0, that's where I am right in the middle of all of those charges. Then the electric field contributions from each side of the ring are just pulling all in different directions, and they cancel out. So that was an interesting case. What about, can we go one step farther? What if we went from having just one charged ring to having a charged disk? Now, the trick there is to say, well, a charged disk is just made up of lots of little rings. And so if I want, I can write the charge on one of those rings as, this is the surface charge, so that's in terms of coulombs per meter squared, and this d area is the area of one of these differential little rings, so that's going to be in meters squared. And so for the area here, I'm going to write it in terms of r, and it's going to be all the way around times a little extra. So 2 pi r gives me how far around it is, and then dr gives me the radial thickness of that ring. Okay, so the way that I build up my charge is by taking the surface charge times this dA. That's the little surface surface area element. Okay, so each one of these rings is going to have a little contribution to the electric field in the z direction. If I have a positively charged ring, it's going to be pushing away on positive charges. And so I start out with this expression for a charged ring, and then for my Q, I'm going to put in this. Okay, so my 2 pi r sigma. Okay, so that's what I do. You're going to go ahead then and integrate from 0 to r to get all of those rings from 0 to r. And this integral, it turns out, is one that we do know how to do. What I would do with it is do a u substitution of z squared plus r squared. Treat z as a constant, and then r is not a constant. And then you would have to do, you'd have to set different limits on the integral, and then your du would be 2r dr, which is perfect. It's that. Okay, so doing this integral is not too hard, and you come up with a very nice expression for your charged disk. Now, something to notice, as z goes to 0 for your charged disk, this is not, in fact, 0. So that's an interesting difference. And another interesting difference is that, well, actually this is the same. It's a little harder to show, but as you get really far out, such that z is much bigger than r squared, z squared is much bigger than r squared, this does go back to looking just like a point charge. Okay, but that's a little bit harder to show. So let's do just a quick example here. It says, at what distance along the central perpendicular axis of a uniformly charged plastic disc of radius 6 meters, 0.6 meters, is the magnitude of the electric field equal to 1/2 of the magnitude of the field at the center of the surface of the disc? Okay, so it's saying you've got a field right here. How far up do you have to go to have 1/2 of that field? Well, to do this, all you need to do is to say, what is your field at height 0? If I stick in 0 for the z, this term goes away, and my electric field is just this big. Okay, now it says where, at what height, so I'm going to be solving for a z, is the magnitude of the electric field equal to 1/2 of that. So I'm going to say 1/2 of this, so 1/2 sigma over 2 epsilon naught equals sigma over 2 epsilon naught times 1 minus z over z squared plus r squared. Okay, now I can multiply both sides by 2 epsilon naught over sigma, and what I find is 1/2 equals 1 minus z over square root of z squared plus r squared. Okay, I'm going to subtract off 1 from both sides and then multiply both sides by -1. This will give me 1/2 equals z over square root of z squared plus r squared. Okay, then we can go ahead and cross multiply and square both sides, and that should give me 4 times z squared plus r squared equals, let me see if I did that right. Oops, no, I did not. It should give me z squared plus r squared equals 4 z squared, or z equals, I'm going to minus a z squared on both sides, and that would give me r squared equals 3z squared, and I would get z equals r over square root of 3. So when you put in now your 0.6 meters and divide it by square root of 3, you're going to get 0.35 meters. Okay, so I gave you a problem on your homework this week that has you look at using this form and making sure that you understand that this is the surface charge in units of coulombs per meter squared. Okay, so on to the main event of today. What is our main focus? We want to think about electric dipoles. And the reason we want to think about electric dipoles is that a lot of materials can be modeled as being formed out of little electric dipoles. Water is a material that has a constant electric or a static dipole moment where you don't have to stretch on it with an electric field. You don't have to put it in an electric field for there already to be a little charge separation between those two hydrogens and the oxygen. So you have a little pointer. And the way that we characterize a dipole field is by the plus and a minus that are equally matched. So the overall dipole has a charge of 0. There's a direction to that dipole because we have the d vector pointing from the minus charge to the plus charge. And so this quantity p, I know it's a little confusing because we also used p for momentum, but this is p dipole moment, is the product of q, the amount of charge on each one of these sides, times d, which is their separation. Okay, now a strange thing about this type of field is that it's pointing in different directions at different areas. So above, so look, here I'll draw my P is pointing this way. There's my P. If I'm up above the dipole, above the E is going to be pointing this way. If I'm down below the dipole, the E is going to be pointing this way. And then if I'm to the sides of the dipole, notice how the field is pointing out from the pluses into the minuses. The E field is going to be pointing opposite the direction of the dipole moment. So it's a little bit strange. On the top and the bottom, it's pointing in the same direction as the dipole moment. Over to the sides, it's pointing opposite the direction of the dipole moment. So yeah, that's why this is a little bit confusing, but it makes sense if you look at the picture. Now, one of the reasons it's important to start thinking about this is that we have been talking about just point charges. In point charges, the electric field dies off as 1 over r squared. However, if you have a dipole, it has a plus and a minus, so there's overall no charge. And when you have overall no charge, that means that you would expect the field to die off more quickly because you don't have that overall charge that's causing the field to not be 0. And as it turns out, well, one way to see it is, let's say that you take a point up here. It's easy to calculate when you're on the same axis. So you have the plus q is slightly closer to the point P than the minus q. So it's going to have a slightly bigger contribution. The electric field is right here. There's that total is going to be this positive contribution minus that negative contribution. And if you do a little bit of algebra, you can find that it's this size. this is d over 2. This is also d over 2. And then our distance z here, this is the z that they're talking about. Well, you notice it has this sort of funny form where it looks like I have a q and a d on top. And as it turns out, I can write my electric field from a dipole in this form, where P is telling me the direction of this, and depending on how far I'm out, I have to figure out what direction the electric field from a dipole is pointing by drawing those field lines. So like, as I said, above the electric field would be pointing this in the direction of the field, below in the direction of the field, and then over to the sides the electric field would be pointing down. These are my electric field. But it turns out it always has this dying off as 1 over r cubed property. Okay, and so this is the size of that electric field is going to be proportional to k over 2 times p over r cubed. So just to give you an example of that, it says the figure below shows an electric field. What are the magnitude and direction relative to the positive direction of the x-axis of the dipole's electric field at point P, located at distance with r much bigger than d? Okay, so you actually know how to do this problem because you could just do this in a straightforward way. Okay, you've got one electric field vector pointing this way. That's from your plus. And then your electric field from the other one would be pointing towards the minus with the same magnitude because they're the same direction, same charge. And then so you could just go ahead and add those vectors up, and you'd get your net vector pointing down. And so I could get that without even thinking about this. On the other hand, it will make it easier if I am able to just use this, because I'll be able to say that the magnitude of that field is going to be very close to the dipole moment, which is just q times d, over how far I am from the center of the dipole. So that would just be r cubed. Okay, so I have a magnitude and the direction is pointing down in the minus y direction. Or if you like, we could write this as minus and then j hat. Okay, so that's an example of using the dipole as the source of an electric field. Now, dipoles are a little bit funny, but this is true of all charges, is that they can be a source of electric field, but they're also acted on by the electric field. Charges produce an electric field in the region, but then they also get pulled on. And so there's kind of a snake eating its own tail aspect to this. Now, the net charge on a dipole is 0, so it's not as though I can put a dipole in a field and expect it to get accelerated in one direction or another. The reason is that the plus side is getting pulled on in a different direction from the minus side of the dipole. However, that does not stop our dipole from experiencing a torque. Remember, a torque is just R cross F, where the force is going to be this. So they're both going to experience the torque in the same direction. It causes the dipole then to spin. So our R in this case would be our d over 2. Our force would be Q times the electric field strength. And so it turns out if you add those together, because this is going to be 1/2 d times F plus, for each one, you're going to get a 1/2 d times E. So this is the d times E is going to be P. That's going to be P, the the dipole moment magnitude. And it turns out we can write this as a vector. So the torque vector on our object is going to depend on P cross E. The torque is going to be biggest when our object is aligned something like this. So if our P is like this and our E is like that, that's when we're going to get the biggest torque. The biggest torque is when I'm most perpendicular to the field, the magnitude of the torque. So what is this torque doing? Essentially, it's trying to get my dipole to line up with the electric field. It wants the dipole to be pointing in the same direction. So there's your minus, there's your plus, and when it's aligned, the torque becomes 0. Now another way to think about this is that because our two little charges in our dipole are each getting pulled on, they can either be getting positive or negative work done on them. Okay, and the electric, if we do that work, in our linear, that was our force times distance. In our angular case, that was torque times angle. And in this case, we can integrate the torque over an angle to find our the amount of force. So when you look at this expression, what it's trying to say is that when I have my plus Q minus Q like this, that's my 0 energy. When I have my plus Q minus Q like this, that has an energy of minus PE. So that's the lowest energy. And then anti-aligned with the field, so that's where I have plus over here and minus over here, that's where I have my biggest energy. U equals plus PE. And the idea there is that this is just like a ball that's at the top of a hill. If it can have its potential energy transformed into kinetic energy. That's the same case here. This has potential energy, and it can get transformed into potential kinetic energy when this gets spun around. So I have given you one problem on your homework with this, just to see what sorts of numbers you would expect to get out of it. Here's a sample dipole question. It says an electric dipole consisting of charges of magnitude 1.50 nanocoulombs. Okay, so I have a plus and a minus. Each one of those is, I have a plus 1.5 nanocoulombs, a minus 1.5 nanocoulombs. So my Q is going to be 1.5 times 10 to the minus 9 coulombs, separated by 6.2 micrometers. So my distance is going to be 6.2 times 10 to the minus 6 meters, is in an electric field of strength 1100 newtons per coulomb. Okay, so they give me my electric field strength as well. So then it asks me, what is the magnitude of the electric dipole moment, and what is the difference between the potential energies for the dipole orientations parallel and anti-parallel to the electric field? Okay, so for part A, it's just asking me to take my Q times my D. That gives me my dipole moment. So it's going to be 1.5 times 10 to the minus 9th coulombs times 6.2 times 10 to the minus 6 meters. And that gives you this 9.3 times 10 to the minus 15th coulombs times meters. Okay, so that's your dipole moment. And then if you want to find your difference between the potential energies, the difference between the potential energies for parallel and anti-parallel, well, if I start out parallel, I'm going to have negative P times E. And then anti-parallel is going to have a positive P times E. So if I want to find the difference between those, it would be essentially PE minus a minus PE equals, and then you're going to have to go ahead and take 9.3 times 10 to the minus 15th coulomb meters times the electric field strength, which is 1100 newtons per coulomb. And the coulombs will drop out, and then you get newtons times meters, which gives you joules, and then that should give you 2.05 times 10 to the minus 11th joules. Now, the reason we're interested in this in terms of just everyday physics is that this is essentially how a microwave works. The electric field in a microwave has a frequency of 2.45 gigahertz, somewhere around there. So that means that the electric field is flipping direction 2.45 billion times every single second. And most of the time, the water molecules in your food are just kind of flip, 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 flip. No problem, but at some times there's a temporary hydrogen bond between three water molecules, and then when that flip happens, the bond is broken, and that temporary hydrogen bond, and the energy that's put in there is transferred to heating the food. Okay, so this is a nice connection to everyday life, where this is the sort of thing that powers your microwave oven. All right, so what did we go over today? We talked about electric field lines. If the electric field lines are closer together, that means that the electric field magnitude is larger. If they're farther apart, it means the electric field magnitude is smaller. We talked about dipoles, which is a plus and a minus charge that are separated by some distance. The dipole moment is the distance between the charges multiplied by the amount of charge, and they die off. The fields from these die off as 1 over r cubed, as opposed to 1 over r squared for your Coulomb's law type of charges. And these are interesting because when you put them in an electric field, instead of pulling one way or the other, if you put your soup in a microwave, it doesn't get pulled to one side of the microwave. Instead, what happens is that the little dipoles experience a torque, and that's related to the orientation of the dipole in the field, just as the potential energy is related to the orientation of the dipole in the field. Okay, so this finishes up our content for chapter 22. We'll be on to chapter 23 on Friday.